Flip tanks can be used to simulate fluids that is confined inside a container with limited supply of water, but what most people don't know is that flip tanks can be used to simulate infinite water flow as well. The best example is a river that occupies a limited space but has infinite water flow. That way you can get to cook your simulation with less water, saving you computing time, and render a scene that looks like it has a lot more water than it actually is simulating from. I'll go over how to create the initial body of water in complex shapes. Then I explain what the boundary layer does and how it works with the waterline. Next, I explain how a surface volume can be used to replace the waterline when using the boundary layer feature for a more precise simulation. Then I demonstrate how to create and set up a velocity field known as a velocity volume to direct the water flow. Last, I explain some simple concepts on how the velocity volume works with the flip solver. This video does require you to know the basics of configuring a flip simulation, as I'm not going to go over the detail into the basics. You also need to understand how the waterline works in the flip solver, but even if you don't know what the waterline feature does, I think you should be fine. My explanations in this video are very detailed. If you're interested, you can learn about the basics of flip tanks and the waterline in my previous video titled Flip Tank Basics for Beginners. I explained the waterline around halfway into that video, so if you only want a refresher on the waterline, you can skip to the middle of that video. But I think if you know the basics of flip tanks, you should be fine for this video. Anyways, a link will be provided in the description below. This is actually created with a similar setup like the teddy bear flip tank sim. They both use flip objects and do not contain a volume source that constantly emits water, which makes the scene very heavy. So let's take a look. This is what we're going to explore through the scene. This is what it'll look like. So this is the river. This is the riverbed. Let me turn off the water. Here. So this is the terrain that I've created where the river flows in this riverbed. Now let's take a look at the simulation first. The simulation setup is actually very similar to a flip tank. You have a flip object. There's no volume source. There's no constant that volume source that we used in a previous video to keep emitting water from, like a faucet. There's no need for that. Sorry. Something funny is going on with my viewport. If you see something like this and you're not sure and everything is correctly hooked up and you're not sure what happened, go to one of your static objects and just toggle the display geometry on and off, and it'll fix it. So back to the river. I'm not going to discuss how I created this terrain, but I really want to discuss how I created this body of water to begin with. This yellow body of water. Let me take out the rocks. So this body of water is something that you need to know how to create. This terrain is out of the scope of this video. I might just make another video for it maybe in the future. Given a terrain you obtained, say you want to generate a body of water flowing along this channel in the middle of the ground. So you want a river. You first need an initial body of water that fits in this riverbed. It should fit nicely like it was made out of a cookie cutter. I'm gonna go over how I created the shape of the initial body of water, which is the most essential part of setting up this scene. So I started with a box. I want to show you, this is the terrain. My box is here. Maybe I'm gonna change the background color so it's a little better. Now I obviously need the box a little bigger. Then I move it down a bit. I make it wider. Then I move the box in place so it matches the riverbed. So as you see, the riverbed is grayed out on the back. This is my box right here. This is my box. Now I wanted water to flow through this river channel here. So that's why I have the box in covering the volume of that river channel. So now I have a general shape of the river channel. I actually linked the box size parameter with the terrain, so if I ever change the terrain size, it would automatically update the box. Now this is where it gets interesting. Let's hide everything. I brought in the riverbed. This is it. And then there's something like a Boolean that you can use. So basically, this is my box. I want this box to be in the shape of this river channel here, sort of like a cookie cutter. So I have this big piece of, you can think of it a big piece of clay, and I'm chipping it away so it fits into this river channel like a puzzle. So the best way to do that is with a Boolean. What the Boolean will do, it will take this piece and subtract the volume, the shape of this riverbed. Wherever this riverbed is, it will subtract it from this box. And what do you end up with? This is what you end up with, which is in the shape of the riverbed, which fits in perfectly. Now, I don't know if you remember, I also had 2 rocks in the middle of the riverbed. So I take this piece, and I need 2 holes here. Water's not gonna be going through these 2 rocks, so I need 2 holes here. So what I do the same thing again. Take this rock and subtract it. So I get a hole. I do that one more time. I get another hole from the other rock. Now this topology is pretty bad. Like, there's barely anything subdividing this on the top. So I'm going to remesh it. I'm not going to click this, render this, because it's going to take a long time to cook. But after I remesh it, it gets really heavy. There's too many polygons. So I do a poly reduce. And then I do a cache right here, so I can load it up faster. So this is what it looks like. Now we can use this as our initial body of water. We can feed, let's go into the .NET. So I've brought in everything I need. The .NET here, the flip object. I actually fed in that initial body of water into here. So Houdini knows what my initial water data is. Again, we use the surface salt. Now, I don't use the water line for that infinite body of water, that illusion of that infinite body of water that I mentioned for the teddy bear simulation. I don't use that. I use the boundary layer instead. The boundary layer refers to the bounds of the volume limit of the flip solver. So this purple box is the boundary limit. Now there's a thin layer on every face of this boundary cube. What the boundary layer does, it keeps refilling this volume of water with more water at the boundary. So at the edges of this box, it'll keep refilling more water, like an infinite flowing faucet, but it's only on the edge. So it's perfect for rivers. So if I didn't specify a surface, say these were blank, it will use the water line as a reference. So anything above the water line at this edge, anything above the water line and at the boundary layer will just get ignored. Nothing will happen to it until water particles reaches outside the volume limit, then either it gets killed or ignored by the sim. Below the waterline, it will keep reseeding these fluid particles. It will keep refilling it. So anything, so for example here on this side of the river, I want water flowing into it. It will reseed all these. It will refill water below this water line at the boundary layer. And above it, it will just ignore. It will just delete it. So that's what the boundary layer will do. The boundary layer only uses the water line if the surface volume is not specified. If the surface volume is blank. But say I do want to specify the surface volume. So I'm going to turn off the water line first. Now, what is the surface volume? To answer that question, we need to go back to the geometry of the initial body of water, where we did a cookie cut with the Boolean node to create the shape of the water. I turned this is a polygon, I turned it into VDB, I turn it into a volume, and then I get the surface volume of the body of water. You can then feed the surface volume into the boundary layer surface volume parameter. This will tell Houdini while you have the water flowing infinitely, try to keep the shape of the water. Surface volume. Now what the surface volume will do is the flip solver will try to maintain this shape of the river by using the boundary layers. Now that's the edge. That's the edge of this cube, of the purple cube right here. At the edges of this purple cube, where it's intersecting this surface volume, it will reseed the water. So new water particles is going to come from that edge. Now you'll say like, well, that's not going to help. We have the boundary layer and the surface volume intersecting in two places. Now I just want water to flow from one side, from this side, and I want water to flow down the river, like from right to left. So that's where this lower padding and upper padding comes in. Now my lower padding is set to 10 and the upper padding is set to 1. I'm just gonna run a few frames so you can see what it looks like. So obviously this is the lower padding right here, and this is the upper padding. So I had this rotated the wrong way. So water is going to flow from this side, from the right side to the left side. The padding defines how thick the boundary layer is. It will reseed the water from. So it will refill the water using all this area. I specified here by 10. That's where from this side. The direction of the water flow will be determined by this velocity volume. So let's go into the velocity volume. Now let's go back to our initial body of water. Now I had cached this out to get a velocity volume out of this polygon. Well, first I need a volume. I need a velocity volume. So that's where I need to instantiate velocity. You drop down a volume node. That instantiates a volume. What do you want to instantiate? What attribute do you want to fill it in with? Velocity. You'll see that this gives me velocity x, velocity y, velocity z. Now, volume can only hold one value in for each. These are called primitives. Each volume, each little icon, this cloud icon here, there's 3 of them. So there's 3 primitives of volumes here. One for each scalar value of the velocity. Velocity has 3 numbers because it's a vector. So you need one primitive to store each number. So that's what this does. But this cube is not helping me because that's not even close to the shape of my river. So that's why we have this match size down. What it does, it takes this velocity volume and tries to match the shape of this river as close as possible. Basically, it's a bounding box. It puts a bounding box in it. Match size will then fill that bounding box with our instantiated volume. So we end up with, so this is the output. Oh, sorry. So we end up with this. 3 velocity primitives in volumes. Now we can feed this into the velocity volume in the flip solver. So as you can see, the volume velocity, we specify the velocity value here, which will determine where the direction and velocity of the river. So the water is going to be flowing in the positive z direction as specified in my velocity. Now after we have the velocity volume all set up, we can feed it into here. So that will tell the flip solver that we want to maintain this surface volume of this shape of this water and have the water moving at this velocity. Now the water is going to be reseeded, so at this edge, basically here, and flow out here. That's where the lower and upper bound padding is specified. What that means is new water is going to flow through here at this specified velocity volume. So what it does is that this surface volume tells it where the water will reseed, where the water is going to be recreated. New water is going to flow in. That volume, that area, will sample the velocity volume here. Because if you remember, the velocity volume is a very large rectangle. This is the velocity volume. It's a very large rectangle. The shape of the river is this. I guess you can't see it. Let me template this. Okay. So the bounding box here is the velocity volume, but the shape of our river is like within this bound. So the water here will sample the velocity volume from this rectangle. Basically, it's going to ask the velocity volume, this rectangle, how fast should I go? I'm over here. I'm right here. I'm this water particle at this position right here. And how fast should I go? It'll ask this volume, velocity volume. So the velocity volume stores the velocity value at every single position in this, within this bounding box. The water particle at a certain position will ask the velocity volume how fast it should go, because the velocity volume has all the velocity values of all the positions. So if you specify the velocity volume, don't forget to enable this apply boundary velocities. So after you have all that set up, you can just play the simulation, have it cooked at the end. Now I have this cooked, pre-cooked and cached, so you can take a look at what it looks like. Let's move back up a bit. I want a top-down view. If you look carefully, you can see that the water is coming from this side, and it's all moving from right to left. And it's just going to continue moving like that infinitely. So this is very handy for creating a river or some sort. So you don't need a fluid emitter and keep emitting particles from this side, which will take forever. This is a good optimization for the river. I don't go over how to extract the simulation data for rendering or how to set up the materials in this video. For more information about Dopp import and rendering the simulation, you can check out this other video I have posted before, which explains the basic concepts for Dopp import, but it uses a different scene for rendering and doesn't use this river scene. Of course, the link will be in the description. However, the workflow and concept is almost exactly the same for rendering and extracting the simulation data. Let me know in the comments below if you want me to demonstrate how to extract this river scene. The reason I didn't include it is because if I did do an explainer video on rendering this river, the content is almost the same as my previous video. But I do admit Houdini is a hard program to learn, and sometimes it's the little things that might get you stuck. Please leave a comment if that happens to you, and I'll make a follow-up video to this one explaining how to extract the sim data out for rendering this river scene. Thanks for watching and sticking to the end.